Hello, welcome back. In the last video, we talked about all the fusions in DeepSeek v4. And in this video, we're going to look at one of these kernels that does the fusion. So in particular, we're going to look at this fuse Take bias kernel, which is a CUDA kernel. And it basically fuses all of these operations together. But before we're looking at the code, let's quickly do an overview of GPU programming. So at a high level, GPUs have these threads that are executing, and they have thousands and thousands of threads that are executing in parallel. And in modern GPUs, we will organize them into warps. So for NVIDIA GPUs, you'll have typically a warp of 32. And these warps, these threads in a warp, all execute collectively. And then these warps are organized into CTAs or blocks, which stands for cooperative thread arrays or blocks. And then these blocks are typically run in parallel on these streaming multiprocessors. And then on GPU, there's actually many streaming multiprocessors, hundreds of streaming multiprocessors. And when we write a particular CUDA kernel, we're actually writing the code that executes here. And as you'll see, we basically have math that takes in the block index and the thread index to branch based on behavior, based on which thread we are. And then lastly, the way that these threads work is they actually have access to various forms of memory. So they have registers, which are going to be the fastest form of memory, but it's going to be the smallest in size and capacity. It also has shared memory, local memory, and it also has global memory. So global memory is your HBM. It's going to be where you have the most capacity to store things, but it's also going to be the slowest to read and write from. Okay, now here what I've done is I've copied all the C++ code for the kernel, and then I've created a summarization pseudocode. So what we're going to do first is we're going to look at the pseudocode to build an intuition as to what's happening, and then we're going to look at the C++ code. So first off, you'll see this grid depth control.wait, and what does this do? So to understand this, we need to come over here, and we need to understand that traditionally in GPUs, kernels run synchronously one after the other. And what this means, though, is that there's a little bit of inefficiency because, for example, imagine you have a gem kernel and a top K kernel. Technically, the top K kernel's first block could start after the gem kernel's first block finishes. But traditionally you can't. And so basically what this code allows you to do is scheduling at a more granular level where you can say, hey, this has a dependency on this, and once this finishes, we can start immediately. And so this allows us pipelining where instead of this much longer execution, you can kind of pipeline it this way. And so what this code is doing is it's effectively running out here, and it's blocking until this one gives the signal to go. Okay, what next? So this code is basically going to be loading from global memory into the registers, and it's doing it via what's called a vectorized load, which is just a more efficient way to load from global memory into registers. If you recall, there's also two different types of routing. There's hash routing, where basically each token deterministically goes to an expert, so you don't need to do any of the top K stuff. And so for that reason, we're just going to ignore that for this video. When we then do normalization of the routing scores, we then do top K, and then we do another normalization, and then we signal to the next kernel that we're done. So at a high level, that's what this kernel is doing. Now let's kind of look at the code. So there's a few things I want to call your attention to. So the first one is that we use these C++ templates to do monomorphization. And what this basically means is we're going to stamp out a bunch of different specialized functions based on things like values per thread, num experts, et cetera, et cetera. And then if we scroll down here, we see the top K gating softplus square root function. And if you're not familiar with GPU programming, this is kind of one of the key ideas, which is, this program is going to be executed on each thread, but there's going to be divergences in the execution based on the block IDX and thread IDX. So remember, you have different blocks and you have different threads. So for example, when this thread executes, the thread index will be 1. When this thread executes, the thread index will be 2. And when this, like let's say 32 thread index executes, it's going to be block 2, thread 32. And so basically this causes the branching and behavior that you'll see as we continue. This is the signaling that we talked about earlier. You'll notice that this like only works for certain CUDA architectures. And other ones you just have the slower like synchronous kernel scheduling. Because we're doing monomorphization, we can actually do compile time dead code elimination. And so this if const expr stuff basically will at compile time only filter the branch that we care about. And these branches are basically the input types. So float, bfloat 16, etc., etc. And this code is doing the vectorized load that we talked about earlier. This is the hash routing stuff, which we won't get into because it's pretty simple. This is the normalization stuff. So it could be worth diving in a little bit here, where basically what this is doing is, if you think about it, like you're kind of dividing the normalization work across multiple threads. So like one thread might do experts like 1 through 4, another thread might do experts like 5 through 9, etc. So after all of this, you're basically going to have all of your scores normalized. And then you go into top K. And how does top K work? So the first thing you're going to do is you're going to calculate the maximum value for a particular thread. So for example, if thread 0 is responsible for 1 through 4, it's going to say, oh, okay, of experts 1 through 4, which one has the maximum value? And so you can see here, that's where that's happening. And then we're going to do this interesting butterfly reduction pattern, where we're going to iterate for threads per row divided by 2. And it's this interesting algorithm where it's almost like merge sort, where you're going to run for a certain number of iterations. For each iteration, 2 threads are going to compare their values and keep the top one. And at the end of all the iterations, you're basically just going to have one max value shared across all of the threads. Once you're done with that reduction, then the first thread group is going to write to global memory. And so this first iteration is going to basically say this is the first top K expert. But sometimes you might have top K equals 2, top K equals 4. And in that case, what you're going to do is you're going to set the routing score to negative 10,000, and then you're going to rerun this algorithm again. And because you set it to negative 10,000, the next one that you picked is going to technically be like the second expert. And you just keep doing this over and over again until you get your top K. And then finally, you apply a normalization, and then you signal so that the next kernel can start this block. So hopefully this was interesting. Obviously, I kind of glossed through some of the more nitty-gritty details, but hopefully this gives you a good overview of what a CUDA kernel kind of looks like. And in future videos, we're going to look at things like Triton kernels and tile line kernels. So yeah, see you in the next one.